Because I won't be here all the fourth period either today. All right, precipitation is not a phase change, okay? When we talked about precipitation way back in the beginning of the semester, we said precipitation was when two liquids made a solid. Sometimes there's a color change associated with it. You took two clear liquids, mixed it together, and made that yellow stuff that was in the test tube, okay? That A had a color change, and it made a solid. That had two indicators of chemical change. That was a precipitate, not a phase change. Yes, ma'am. Probably not, but it's okay. Go ahead and ask. Rain is a different form of precipitate. Okay, we use the word precipitate all the time. Rain is condensation. Okay, that's part of the water cycle. Okay, when I use the word precipitate in chemistry class, I'm not talking about the water cycle in rain. Okay? If I was going to say that, I'd say we're condensating outside.
What's that anyway?
Aqueous? Aqueous. That's just a state of water. Well, it's not really water. It's when you dissolve something in water.
Oh,
Okay? Water itself is a liquid. But if you had coffee today, if you had tea today, if you had soda today, if you had orange juice today, if you had milk today, Kool-Aid today, Gatorade today, almost anything to drink this morning with the exception of water, you had something that was aqueous. Because it was dissolved in water. Okay? Now, the state changes that you guys listed. Let's just start at the top. Let's take freezing. Okay? Most of you can tell me that freezing starts in what state? Okay? And it changes to a what? All right. Everybody can tell me that a liquid changes to a solid. You learned that in another science class. That's the only part that you know from another science class. Today we need to talk about the energy changes. Is it endo or exothermic? We need to write its thermochemical equation, and we need to be able to calculate its Q and place it on a graph. Okay, that's the part that goes with the chemistry lesson. So, when you think about, and I'm not going to draw these pictures and all these phase changes today. All right, but if you think about the way the liquid looks, and you think about the way a solid looks, no, the size of the particles don't change. Okay, the size of the particles stay the same. I tend to draw them different because I get sick of drawing the particles in the solid. So I tried to draw them similar, but you can tell I got a little messy and they're not quite the same. Okay, so let me put a little side note up here. Size of particles are same. Yep, because it's the same compound. And remember, we're just changing the state, so it's the same compound. For the purposes of this discussion, it could be water. Okay?
But water freezes, but you can freeze it in a container and freeze it and make it air that will crack.
Because air gets trapped.
Oh.
I thought it did.
I know, like that. Yeah.
It freezes in an hexagonal pattern. That's why. So if you're smart, crack a bottle, drink a little out, pour a little out, stick it back in, and when it freezes, it won't crack the container.
Wow. You know, hopefully my water bottle is both.
Hopefully not.
All
right, so if we look at this, all right, so we've got liquid, we become a solid, right? So what has to happen to the molecule? Do they have to go faster or do they have to go slower? Okay. So if it has to go slower, does heat have to be released or does heat have to be absorbed? Okay. If we absorb the heat, take it in, the particles are going to start to do what? Move faster. If you move them faster, are we going to become a solid? No. Okay? You want the particles to slow down, you said. So heat has to be released. If heat has to be released, all right, the heat has to be on this side. Okay? So, all right, so heat is released. If heat is released, based on what we learned earlier this semester, what do we know? Is it endothermic or is it exothermic? It is exothermic. Okay? Now, when we write the thermochemical equation, all right, this has a name. It's called a thermochemical equation. You can do it with numbers, or you can just do it with the word heat. Doesn't matter which way you do it. We're not going to do it with numbers today. We will down the road. All right? Okay, so what's on the left? What's on the left?
Oh, liquid.
Okay. Okay, so we got liquid. All right. What's on the right? What's on the product side? All right. And then plus heat. Now, a basic rule of thumb. Every time heat is a product, it is exothermic. Okay? Whether it says heat or whether there's a number on the product side, it doesn't matter. But every time you see heat as a product, it tells you it's exothermic. Are you with me on that? Okay. Now I'm trying to show you an arrow. Why? You gotta draw what? You didn't put an arrow on it? Oh, well, at the end of class, just remind me to bring back the arrow. I will not come again. All right, everybody caught up?
Yeah, anyway, they have a Google Doc called for the.
I know 2 dashes and a greater than sign.
Yeah, that's not.
Or special formatting, the character, and the insert. Yeah.
I just went the lazy man today, so because I don't know how to do the other stuff. All right, what's the opposite of freezing?
No. Oh, this one.
Yeah.
Like, hard eyes.
Your hand is warm. Heat transfers from your hand to the ice. So your hand is going to lose thermal energy. So the particles in your hand are going to slow down. They slow down, yes. Then they go slower. All right. So melting goes from a what to a what? All right. So basically, we're starting in the solid state where everything is. This is the last set of pictures I'm going to draw. All right. And we're going to a liquid. So we know that we have to do what to get this to happen? We have to heat it up, right? Okay. So we have to heat up. So if we've got to heat it up to get the particles to move, Sean said we had to do what to it? We got to absorb it, right? So if we have to absorb it, we have to add heat on this side. Okay? So anytime we said heat up, that means absorb. So if we want to write the thermochemical equation, what do we start with on the reactant side? What's over here on the reactant side? Solid, okay, plus heat, and what do I become? A liquid. Now, again, just like before, because this is a reactant, that tells us what? It's endothermic. Okay, that tells us it's endothermic. Everybody okay with that? So what now? Okay. All right. Does everybody have it?
I think yesterday I was at Walmart. I think
So what now?
they had a silver one.
Yeah. All right. So give me another state change you gave me a second ago. All right. Let's hold that one. Get one of the other normal ones. All right. Number 3, condensation. Condensation goes from a what to a what? Gas to liquid. This is the one people usually refer to as sweating on the outside of a glass. All right, so if we have a gas and we change to a liquid state, all right, the particles are moving really fast. All right, they're moving fast here, and they have to do what to become a liquid? They have to slow down. Okay, so they have to go from fast to slower, right? So what do you need to happen in order for the particles to go from fast moving to slower moving? They got to lose heat, okay? So if they have to lose heat, what does that mean they need to do? Do they need to absorb it, or do they need to give it off and release it? They need to release it. So if they need to release heat, it needs to be where? Needs to be a product. You've got gas, goes to liquid, plus heat. So based on where the heat is, that's what kind of reaction? Exothermic. It's right here. It tells us it's exothermic. All right. Anytime you release heat, it's exothermic. The heat is on the right, or the product side, so it's exothermic. When you gain, it's endo. If you write it on the reactive side, it's endo. All right, we caught up? It is. All right, so the opposite. All right, most people do not refer to it as vaporization. But we're going to call it vaporization. You'll see this, unfortunately, if you have to watch the videos, be talking about this. Hopefully, I'll still be here, but I can't. All right. Evaporation and boiling. There's a huge difference between the two, and I'll explain that, unfortunately, in the videos. There's 6. Evaporation, I'm just going to put up here, is a non-boiling liquid to illustrate the difference. You don't think I'm crazy. All right. But evaporation is specifically a non-boiling liquid. Now, if you went home and told me that you heated some water on the stove to make spaghetti, most of you are going to turn the burner on to what? And if all the water went away and you came in and told me it evaporated out of the pan, would I know what you were talking about? Yes, I know what you're talking about. Now, you technically vaporized all of the water out of the pan. However, would most people tell me you vaporized all the water out of the pan? No, you would tell me you evaporated it all out. I would know what you were talking about But is that the correct vocabulary? No. Exactly. Okay? When water evaporates, it is a non-boiling liquid. So, water's on the road today. It's going to do what outside? It's going to evaporate. It's cold out, but that water is still going to evaporate. In the summertime, it gets hot outside. It might even hit 100 degrees outside. Is water going to bubble on the street? If it does, do not put your feet in it, okay? That water is still going to evaporate. The only place water is going to boil is going to be where? On a stove, okay? However, if you tell me the water evaporated on the stove, I'm still going to know what you mean. But the correct definition of the word is it vaporized, okay? Now, we'll talk about the differences in these, hopefully with me, but if not in the video. Now, it still changes from a liquid to a gas. That part has not changed. Now, we absorb or release heat. What do we have to do to make a liquid change to a gas? Do we need the molecules to move faster, or do we need them to slow down?
Faster.
Need them to move faster. So, if we need them to go faster, do we need them to absorb the heat, or do we need them to release the heat? We need them to absorb. So, if we need them to absorb the heat, do we add it to the liquid side, or do we add it to the gas side? We add it to the liquid side. So, my thermochemical equation has to say heat plus liquid goes to a gas. And that would be, I was forgetting to do that because it is here. That tells us it is endothermic. Everybody with me on the first four? Now, most teachers teach the first four. The last two would depend entirely on your background in science class. Now, the final two are sublimation and deposition. No, change it from a gas back to a solid. All right, has everyone had an opportunity to get everything, or do I need to wait? Okay. I would have to look it up. I have absolutely no idea. You would think after all these years I would keep one of those in my head, but I forget it every time after I've looked it up. I think it's just age. But feel free to look one up and share it with us again. I tell people to do it every year, and I just can't retain it. It's essentially got to do with the temperature at which something heats, yes. Okay, so you know water. Water will boil at what temperature? And that's on the Fahrenheit scale. So if we're talking water, my color here, if we're talking water out to the side here, we know boiling for water is 212 on the Fahrenheit scale and 100 on the Celsius scale. So if it's like today, and it's only supposed to get up to, I think, like 43, the water on the roads will drop, okay? So it's not going to boil. So if the water dries, it did what? We refer to it as evaporate. But if you put the water on the stove and you bring it to a boil and it gets to 100 degrees, or even really the boiling temperature is really an average. Those numbers are averages. It depends on atmospheric pressure as to whether it boils more or less than 100 degrees. Okay? So that's just an average. If we go to the mountains, less. If we go to the coast, the boiling point will be slightly more because atmospheric pressure will be different. Okay? But boiling itself will be higher because it's on the stove. It's going to reach a higher temperature. Okay? But it just depends on the temperature. Yeah. Yeah. So Nada was going to give us a real example.
I got it.
Okay, give me a real example.
Well, one example of this is the process by which the subterranean air, water vapor can directly to ice without substitution.
Okay, sub-breathing air.
Oh, that's like the water vapor. Yeah.
There you go.
All right, in that air and that atmosphere, whatever it's called, it's like a little water vapor.
Yeah. I thought you were gonna give me something that wasn't just water vapor, but that'll work.
Why are they getting more than water? That's all we know.
All right, so, because for sublimation, the one I use isn't water vapor. All right, sublimation changes from a solid directly into a gas. It's the opposite of deposition. All right, sublimation changes from a solid to a gas. So, again, do we want the particles to go faster or slower? Want them to go faster. So, if we want the particles to go faster, do we have to add heat or remove heat? We have to add heat. So, if we have to add heat, that means we're going to put it on the solid side, right? So we're going to have heat plus solid yields the gas. So we know that this is endothermic. Now, the example that I often use here, because a lot of people can't relate to this, is dry ice. All right, those of you who are familiar with dry ice know that is solid carbon dioxide. All right, solid carbon dioxide will automatically change into gaseous carbon dioxide. A lot of people will use this as a substitute for ice in coolers because it keeps things very cold. Plus, it does not make a mess. Ice, melts in the water, and it really makes a mess in coolers. Dry ice does not. It also works great with fog to make fog machines in a lot of football games. So, yes, so a lot of people use that for, works great in theater, forget the football game. It works great in theater. Okay, sorry, did not mean to slight the theater. Say what now? Okay, there you go, works great there too. All right, the nice thing about dry ice is it's very cold. Your tongue is going to stick to it. I believe so. It's very cold. Okay. Now, the opposite is deposition. Yep. Okay, deposition changes the opposite direction. So we're going from a gas back into a solid. So here, we want things to do what? We want things to slow down, right? So if we want things to slow down, we want the particles to do what? To lose heat. Okay? So if we want things to lose heat, we need it to be what?
On the right.
On the right. We need it to be lost. So we want gas goes to solid plus heat. So this tells us it is exothermic. Everybody with us? Yes or no? Uh-huh.
Yes.
Okay. Okay. As long as when you look at it later, you know what you meant.
I love that.
Yes, ma'am?
Would
Would what? It's shattered. You can turn a banana into a hammer. Did they do that? Turn a banana into a hammer. Yeah, you can do that too. All right.
Oh, yeah. They sell it to the public.
No. All right, if you will, I have this labeled right. Make sure I do. I'm having a senior moment. It happens more and more as I get old. Yeah, I did it right. All right, if you will, Don't draw it really tiny, because I'm gonna put labels on all 5 flat spots, or all 5 spots. 2 flat spots. I mean, yeah, maybe a quarter.
Well, you said don't draw it tiny.
Well, you know, some people make it fit like on 4 lines.
Well, I was gonna make it like,
Yeah, well,
Alright, and I'm gonna label them A, B, C, D, E, so that I can label what the spots are and refer to them. So A is like that spot going up, B is the flat spot, C is going up, D is the flat spot, and E is going up. Now, the nice thing about phase change graphs is they always look the same. They're always safe. The only question is if they're going to go up or go down. If they go down, it's the exact same thing except in reverse. Okay? They always start with the exact same point. E is still at the top, A is still at the bottom, even if it is in reverse. Okay? Now, E is still at the top. Okay, so even if this graph, if I draw it in reverse, even if I do this, and I still have it labeled E, B, C, B, A, it still is all the same points. Okay? E is still going to be the same thing that it is here, and A is still going to be the same thing that it is there. Nothing's going to change. Exactly. That's what I'm telling you. Doesn't matter. It's the same graph, even in reverse. Okay? Doesn't matter, except positive and negative slopes. That's it. Now, if we look here, this is the solid state. I'm going to write something else in just a second. This is the liquid state. This is the gas. Now, tell me what all 3 of those states are doing based on the y-axis. They're being heated. Okay? The y-axis is temperature. All 3 of those spots are doing what based on the line? They're going up. The temperature is increasing. So in A, the solid is heated. In C, the liquid is heated. In E, the gas is heated. Now, are any 3 of those phase changes if they're being heated? Okay? They're not changing states. They're being heated. Now, D and B are your phase changes. B is your melting point and your freezing point. It is your phase change. Okay? At B, we change between what 2 states? Solid and liquid. What can you tell me about the temperature at B? It's the same. So does the temperature change when we melt and when we freeze? No. The temperature stays the same when we melt and freeze. What changes when we melt and when we freeze? The energy changes when we melt and freeze. The temperature does what? Stays the same. It's constant. Temperature doesn't change. It stays the same. Are you with me on that? Okay. This up here is boiling point, evaporation, and condensation. All right, that right there is boiling point, evaporation, and condensation. That is another phase change. You can recognize the phase changes because they're always what? They're always flat. The phase changes never change. They're always flat. Okay? Now, what 2 phase changes are never on a phase change graph? Sublimation and deposition are never on a phase change graph. You can't jump from a solid to a gas. You got to go through the liquid phase on this. they're going to be on a phase diagram, which is different than a phase change graph. Okay? Everybody got it? All right. Now, on this one, if it's in reverse, what's E? It's still a gas. Gases are always going to have the greatest what? So they're always at the top. What's always going to have the lowest temperature? So a solid is always going to be where? And C is always the liquid. So D will be a phase change between the and the yes. Away. All right. B will always be a phase change between the. So did the graph change when I wrote it backwards? It never changes. You with me? All right. Normally I would stop and practice when you talk about Q. All right. We got to calculate Q, and I've got a little over 20 minutes to do it. Get out at 10:35.
Well, we're an hour.
We're on the delay schedule, people.
It feels like it's time to go home. I know, it feels like 4.
All right. Now, on this graph, right here, you guys just heard. Right here, we can calculate the Q and I'm just labeling it. Okay? The same graph. Now, this one will have the heat of fusion, and this one will have the heat of vaporization. All right, it says Q equals MHF on that one, and Q equals MHZ on the top one. Okay, so the top one's called heat of vaporization, and the bottom one's called heat of fusion. Now, because Q is an energy or a heat, and the phase change only loses or changes heat, not temperature, we have to be able to calculate the amount of heat energy that's lost or gained. Okay? Where? I'm just telling you how this is related. Okay? This graph that we just drew, okay? We said this point didn't change temperature, right? It changed in energy. Energy is another fancy word for, go back. It's another fancy word for what? Heat. You have to be able to calculate how much heat is gained or lost, okay? If we draw this graph, heat is gained. If we have this graph, heat is lost. You have to be able to calculate the amount of heat on these flat spots, okay? These are the equations that go with the flat spots. We have to figure out how to calculate with those equations today, okay? So if we're calculating this flat spot, is this equation. If we're calculating with this flat spot, is that equation. I don't care. I'm just telling you that's what each equation goes with. This flat spot is based on heat of fusion. This flat spot is based on heat of vaporization. That's why I rewrote it. That's an F. I wrote it bigger and plainer for you people.
I didn't struggle with that. I know.
It says vaporization. It doesn't say J up there. A check. Again, it says vaporization.
I mean,
All right. Y'all stop whining. Now, Q, we've already talked about this semester, is heat, loss, or gain. And it's calculated to what unit? Joule. Okay? Now, if we were in the US, it could be calculated in calories. All right? We're not going to calculate in calories. On our practice sheet, I do have one in calories, just so you see it. But for the most part, it's in joules because that's the SI unit. M stands for
Mass.
thank God. Mass, which is in what unit? Whew. And HV stands for heat of vaporization. Now, this is a constant. This is on the reference table. Okay? On the reference table. You don't even have to memorize it. You just got to look it up. Oh, you haven't learned it yet. So, if you look on the front page of your reference table, this is in chart 2 on the reference table. Chart 2, in the middle. There's one number that we're going to review in a moment, which is called specific heat, because I'm going to run through that for those of you who forgot. It's been a while. All right. And then there's heat of vaporization and heat of fusion. The shot. Huh? Cal. C-A-L. All right. So if you look up heat of vaporization, the states in their infinite wisdom has decided that we're only doing water. Once upon a time, there was a chart that had multiple heat of vaporization, multiple heat of fusion, and you actually had to figure out what compound they gave you and read the table to figure out which heat of vaporization or what heat of fusion they're using. Once upon a time. Well, they decided y'all were too dumb to figure that out right here. So they eliminated all that stuff. Now they have decided that y'all only have to know water. So if you read a question that talks about Q, you either have specific heat, you have heat of fusion, or heat of vaporization. So it's going to be one of those numbers in that table. Narrowed it right down for you. Okay? So if you read a question that has Q in it, what are the keywords that are going to say to me, oh, I need to use heat of vaporization? Does it say boil?
Or evaporate.
Does it say evaporate? Does it say condense? If it says any of those things, then I'm going to look up HV on that reference table, and I'm going to use what number? Exactly. I'm going to look up that number on the reference table, and I'm going to put it in. If they don't use those words in my question, I'm not using that. Now, if I have this, I already know what Q is. I already know what M is. HF stands for heat of fusion. Fusion means solid. Okay? Solid. Again, it's on the reference table. So, what keywords would we look up here? What words go with solid? Freeze. Freeze and melt primarily. Okay, so if I see freeze or melt, what number is on the reference table for HF? 334. Where are we getting these numbers, my man said? Chart. You can't find this little chart. That would be why you can't find the number. Okay. That helps tremendously. Oh, I see it right there. Right there. Heat of fusion, heat of vaporization, right there. Anybody else struggle? Just a side note, it helps me on the chart. Now, everybody got that? Okay, then when you have it.
They got it.
I don't know why those words freeze and melt. It's like,
You got it? Alright, so, to review just briefly, we did this formula. That's your sugar. Alright? That was heat. That was math. What are these two again?
oh, one more time.
Right, so specific heat and change in temperature. Both of those answers were spent. So, where do we find specific heat? Because some of us got this wrong on that benchmark a while ago. On the reference table, in that same block, you just found heat of vaporization and heat of fusion in. Now, when we did the correction, just point out, several of you said to me this law, which number do I use? If it says water, you should use which number? The one that says liquid, okay? If it says ice, then you should pick the one that has the solid. And if it says steam, you should pick the one that has gas, okay? But if it just says water, pick the one that has the liquid state. Now, how is this formula different from these two that we just wrote down? There's one obvious difference that should slap you when you go to work. These two and this one, the degrees, okay? This one has a change of temperature, meaning you have to do what with the two temperatures? Subtract. These two have no what? Now, what if they say that the melting point is 0 degrees Celsius? It gave you a temperature. Are you going to plug in the temperature? No. Because is 0 degrees Celsius a change? No, they're just telling you what the temperature is. So let's try a couple. Make sure we're all on the same page. And then I'll feel at least like we got most of what I wanted done today.
I know all of it. Like all that, I don't know how we're like. I just met an aunt yesterday. I'm like, wow. My dad has to make no, my grandpa, he would have had like, my grandpa was of 7, but he would have had what he would have died from the doctor in Mexico. Weren't that good back in the day? The birthday school? No.
We need to have time to do at least 2. So you will write it down right back.
All that other words.
Just depends on your work. Some people might use those other words.
How?
So then, I
This is the only problem we do. It does not require Kelvin. Because when you find a difference, it doesn't matter if you subtract the two numbers from Kelvin and the two numbers from Celsius, because you're always trying to get different.
So, if we one number in Kelvin,
Then you have to match. So no one does that. I mean, I guess it would be cool to do that, but I've never seen anyone do that before. All right, so you go solve it. How are you going to know which formula to pick? What jumps out at you with the question?
yes.
As soon as you look at this question, this right here should jump out at you. It screams to you. This says delta T. As soon as you read that and it says 35 to 85, that should say to you, oh, that's a delta T. I'm changing temperature. Okay? So this should tell you, this is an old question, and I'm using Q equals M. Then I'm using that formula. Okay? So, if I'm looking for how many joules, I'm solving for Q. My mass is what? My change in temperature is what? 35 minus 85 is 50. Remember, I'm always using a positive difference. Now, my CP, I find where? Reference table. What did I use here? I used water. So what is water's CP? It's on the very first page. Okay? Or 0.18. Because that is liquid water. 2.05 is ice. A lot of people want to grab that. Okay? So, when you multiply that together, what do we get? Somebody do that for me. I don't have a calculator out. Okay? And joules is my answer. Questions about how we did it or why we picked that formula? Anybody? Let's try a question. Oh, where's the number coming from? Show him, Catherine. Okay, everybody good with where the number came from? All right. So, this one's different. Look at the difference. 3,135. All right, look at that. All right, this one's different. So we're going to do this one, then I'm going to hand out homework, and then we'll be done. I don't do that. Dr. you actually write anything down? No. Yeah. All right. So when you look at these, ignore Tyshawn. He just handed out paper. What about this question tells you it's different than the last? All right. It gives you a temperature which throws people off sometimes. Is this a change? No. All right. It's not a change. But let's say for a moment that you went to plug it in. I wouldn't write this down if I were y'all. All right, let's say you went to plug it in, and you plugged in your 25.2, your 4.18, and then you put in your 0. What's going to happen when you multiply that? You're going to get 0. Is the answer going to be 0? No. All right, so that's not a temperature change. So what's the key word right here? It freezes. So that tells you it's Q equals MHF. So we're looking for Q. My mass is what? And my HF is what? 334. So Q equals what I get when I did that? 8,517. And then joules. Questions about how to find the answer? Because it's freezing, we use that formula. Yes, if it said evaporate or condense, then we would pick HD. But because it said freezing and has 0 degrees Celsius, those indicators are for fusion. Okay? Question. All right. Now, our quiz will not be until Wednesday. Your quiz is largely on Friday and today. I think there's one question on equilibrium on the quiz. Guys, put the calculators in the tub. Well, we have it tomorrow. It was supposed to be tomorrow, but it will be Wednesday because fourth period is behind. And I'm not typing up or sending two separate lessons. So. Huh? No, you're doing the graph on the front that says that you're doing all the math, but you're only doing this graph. Everybody say it? Just the first side. The side that says bullet point, we haven't gotten that yet. I will sign that through the sub, most likely. No. You're doing the phase shape graph. The one that says equilibrium bagel for all the math, and then no, do not do the graph that says equilibrium bagel pressure. Or bagel pressure and water. You don't know how to do it yet. Huh? I have no idea. I'm in the car. The car. No, but like it was so big. I was like, what? I put it in my phone. All right, y'all put your calculator in. Put your calculators up, please.